Perfect.
Okay, good. So yeah, so this talk it definitely has a more, let's say, application flavor than what we saw this morning, maybe, but some methodological aspects will come toward the end, especially in the open questions. I do have a slide on open questions, looking for possible suggestions from you guys. So this is the summary of a work that I have been doing together with Chiara Piazzola, who's a postdoc with me at CNR Imati in Pavia. And then these other guys, Riccardo Pellegrini, Riccardo Broglia, Andrea Serrani, and Matteo Diez, instead they are based in Rome, and they are in another institute of CNR, is the Institute of Marine Engineering, INM. And they have this very interesting, I would say, very practical problem. And the idea of the work was to test two different methods and see how they perform on a, let's say, I would say, realistic application. So this is what I'm going to talk about. We want to do forward UQ for ship performance. So this is the kind of ship we are thinking of. It's a ferry. It's called the ROPAX ferry in the engineering jargon. It's actually ROPAX means roll on, roll off passengers, because people and cars, they get on board of the ship on their own wheels from the back, rather than being carried in and out with a crane. Okay, and this ferry goes in straight advancement in calm water. And we are interested in quantifying the certainty on the resistance to advancement, which is the naval equivalent of the drag coefficient of an airplane. Okay, so really the resistance to advancement in water of the ship. And of course, this depends on a bunch of operational or environmental parameters that are, of course, highly uncertain, right? The speed, the sea state, the payload of the ship, they are all highly uncertain. So we take the classical paradigm of forward UQ. So we have a bunch of parameters. This bunch of parameters are fed into a PDE solver. In our case, it's the unsteady Navier Stokes equations. And out of this unsteady Navier Stokes equation, we compute the advancement resistance by integrating the pressure of the water on the part of the hull of the boat which is underwater, essentially. So what kind of parameters are we focusing on? This is a relatively low-dimensional problem, so we're considering only two parameters. The speed of the boat and the draft of the boat. The draft of the boat is the vertical displacement due to the ship being carried with a certain payload. The payload being the number of people and the number of cars you put in the boat. Okay. We consider the speed to be within the operational range of the boat, and the draft to be plus or minus 10% of the design draft. That would correspond essentially more or less to plus or minus 15% of the design payload. And because we have no special assumptions on these two parameters, we assume them just to be uniform random variables. And this is just to give an idea of the dimensions of the boat. This is a vertical cross section of the boat. The boat is 160 meters long, and the speed range is 12 to 26 knots, and the draft range is 6.5 to 7.8 meters. We actually don't solve things here on this full scale. We actually solve on model scale. The model scale is the size of the wooden model that the guys in Rome actually put in their naval artificial pool. That would be the equivalent of a wind tunnel. They have a so-called naval pool where they do experiments. This is the size of the wooden model of the boat that they put into this naval pool. Okay, so, and then of course, what we want to do forward UQ. So we sample the parameter space. The parameters are denoted by y. Y vector is a vector of two components. Y1 is the speed and Y2 is the draft. We sample the parameter space, we get the corresponding values of the advanced resistance by solving the unsteady Navier Stokes equation. And that's what we want to do, right? We want to do the compute the statistical moments, or ideally the full PDF of the water resistance to advancement. And the goal, or the methodology that we use is that we don't do pure sampling. So this is not a multi-level Monte Carlo. It's going to be a surrogate model-based forward UQ analysis. So we will somehow interpolate the samples here, and we will create a surrogate model, and then we will sample the surrogate model to get the PDF of the resistance to advancement. And of course, we want to do this in a multi-fidelity way. Why? Well, because we're going to solve this for each sample. Each sample requires to solve an unsteady Navier Stokes equation. It's, by the way, also free surface Navier Stokes. Although we don't do direct Navier Stokes, we do runs. Still, a runs call can be computationally intensive. The reference mesh that we're considering takes a few hours in a computing center. It's not something you do on your laptop. So we need to go towards a multi-fidelity approach, and we will consider in particular a hierarchy of meshes, and each mesh will constitute a different fidelity for our approximation. And we do what we all know is multi-fidelity. So we explore the bulk of the variability of the resistance due to the random parameters with many queries to the cheap models, and then we will correct these estimates with a handful of queries to the high fidelity models. But this is all pretty standard. And we do this in a surrogate, with a surrogate model. So before dwelling into the actual surrogate models that we're going to use, I want to spend a couple of words on the run solver that we are using. As I said, we're going to solve the unsteady Navier Stokes equations with free surface. And we are going to do this with a finite volume solver called KeyNavis, developed at Rome. It's a rather established solver by now. It's a second order finite volume scheme. It's a multi-grid solver. And the intermediate grids are actually the grids that we're using for the intermediate fidelities of our multi-fidelity approach. We consider specifically 4 grids that we get by the dyadic derefinement of the reference grid. So the reference grid is this one on the left. You see a zoom here on the bulb of the boat. This mesh has 5.5 million volumes, and we derefine this dyadically. So we merge every 2 consecutive elements in each direction 3 times up to the coarsest mesh. This one here on the right, the coarsest mesh has 11K volumes. So, and then the cost, we assume that the cost of solving the PD over a mesh is linearly proportional to the number of elements in the mesh. So this is cost 1, the second one is cost 8, cost 64, and cost 512. So there's a huge difference in cost between the coarsest and the most refined mesh. And okay, this is the domain, the full domain, and the full mesh. So this is the boat here on the top left here. The bulb is here, and you see that this is the computational domain. We're actually solving half ship. The other half is symmetric. So we do a vertical cut. We always solve the left hand of the boat. We get more space behind the boat to solve the wake. And here you see that the grid that we're using is a multi-block grid, and the multi-blocks are overlapping. So this is quite a work of doing a mesh here. Takes a while, let's say. These are a couple of snapshots of a couple of specific solutions of the solver, just to see that everything works and gives reasonable results. So here you see 4 snapshots. These are 4 solutions. This is low speed and low draft. Here, if you go in this direction, you get a heavier boat that goes much more into water. And if you go from above to below, you get a faster boat. So you see that depending on the payload and on the speed, you get different kind of waves behind the boat, but everything is pretty accurate. Let's say the colleagues in the naval engineering department say that this is a fairly accurate result. So everything works fine, and this is a zoom on the bulb of the boat, and you see that depending on whether you are going slow or going fast, and depending on the draft, the bulb is partially emerging from the water or is completely underwater. Okay, now the main, the idea of this talk is to present not just one, but two multi-fidelity methods, and to see which multi-fidelity method suits better the needs of this practical problem. So let me start with method one. Method one is the multi-index stochastic collocation. Method two will be this multi-fidelity radial basis function. Now, MISC method one, I mean, if you want, I can give you a too long didn't read version, right? The very short and super compact description of MISC is, it's like stochastic collocation of sparse grids, but now we have one or more multi-indices, or indices actually, that govern the spatial refinement. So we are sparsifying over space and parameters if you want. In our case, actually, we have only one index in space. It's one index that chooses whether we're resolving on mesh 1, 2, 3, or 4. So the index in space, we select either this mesh or these other three meshes. So in our specific case, we're not actually doing sparsification in space, but in general, MISC allows you to do sparsification in space as well. So you would create the usual delta operators, delta in the parametric space, delta in the spatial refinement, and you would do the usual sparse grid approach. Now, if you are familiar with sparse grids, this is nothing special. If you are not familiar with sparse grids, I thought it would be better to give you the gist of the idea rather than to give you the formulas, just to give you, again, the rough idea of how this works. So this is what I'm gonna do now. I'm gonna give you an idea of how MISC works without too many formulas, let's say. So imagine a very simple setting where you only have 4 possible discretizations. I call them C, Q, P, and F. And you select which of these 4 discretizations by tuning, I would say with 2 knobs. You have 2 knobs. One knob selects the accuracy of the PDA solver, so essentially gives you which mesh you're using. Imagine you're using only 2 meshes, not 4, but only 2. And here you have another knob that gives you the parametric accuracy. So how many samples on the parametric space you are considering. And here, by parametric accuracy, I'm very broad, and I'm thinking here of either interpolation or quadrature on the parametric domain. Doesn't really matter at this point. So the C, the coarse discretization, is a discretization that you get by doing only a few samples on the coarse mesh. If you increase the mesh but keep a limited number of samples, you get Q. If instead you keep the coarse mesh but increase the number of samples, you get P. And if you do both things, you get F. And ideally, you want to get F. You want to solve a lot of samples on a fine mesh, but this is computationally unreachable. So what you want to do, you want to get somehow an approximation of F out of the other possible discretizations. So how this works in a very naive, or let's say, without hiding a lot of details under the carpet, let's say. But you start from the finer discretization F that you want, and then you add and subtract all the other discretization that you get. This is a telescopic equality. Then you rearrange the thing, and you get that F is the coarse discretization plus this P minus C, the correction you get from increasing the number of samples. There's Q minus C, which is the correction you get by increasing the solver accuracy. You're so passing to a fine mesh, but without adding new samples in the parametric space. And then there's the remaining correction. And, well, there's a simplification to be done here. But the most important thing is that the usual way we do in sparse grids is that we assume that we have reasons to believe that this correction here, this F minus P plus Q minus C, this one is a second order correction. It's small but expensive to be computed under suitable regularity assumptions. So often the idea is, let's just drop this second order correction, And then what you're left with is, as I said, that you can approximate the full approximation as a linear combination of 3 other coarser approximations. They are cheap because they are cheaper, let's say, or cheapish. They are cheaper than F. None of them is particularly accurate per se, because either it sacrifices accuracy in PDE or it sacrifices accuracy in the sampling. But if you combine them suitably, then you get a good approximation of the target approximation. And you get what we wanted. We get the sparsification idea. So you get a lot of samples on a coarse mesh and a bunch of samples, but not too many on the fine mesh. And if you do this carefully, you can also balance the errors in solver and in the parametric space. So in the end, what you do is, instead of sampling a lot of times the PDA solver for many combination of parameters over the fine mesh, what you do is you do a bunch of solvers, a bunch of calls to the solver, the fine solver on a coarser mesh, and then you correct. You see here, either you refine in space here, or you refine in probability here, and then you subtract the coarsest approximation. And here again, I haven't told you whether I'm going to do interpolation or quadrature on this parametric space. It doesn't really matter at this point. These are the usual choices, though. It's the usual Clenchard-Curtis interpolation or Clenchard-Curtis quadrature, Leia. You can do whatever you want here. Of course, the game easily extends if you have multiple parameters. Like in our case, we have 2 parameters. So you would have, you could choose whether to increase the parametric sampling along parameter 1 or parameter 2. And then if you have more than, in principle, if you have a solver that allows you to tensorize in space, so you have a perfect tensor structure in your solver, which we don't have because we have multi-lap overlapping grids. But if you have a perfectly tensorizable solver, you could also play the game of refining only one direction of the mesh or the other. And then if you end up with a lot of possible combinations that you want to choose from. And how do you do that in practice? Well, you do this with the usual Gersten-Gribel adaptive algorithm. So you start from the initial coarse discretization, you refine once in probability or in the parametric space and once in the PD solver, and then say that it turns out that it's more effective to increase the parametric accuracy, then you keep iterating along this direction. So you further sample in the parametric space, then maybe you see that this point is more effective to increase the solver, and then you get further on, okay? This algorithm is not ideal in the sense that it's a fully a posteriori, so you need to solve the PDEs first, and then maybe you realize that some PDEs were useless. So there's an edge to improvement here. The talk of Feischl this morning gave you, in a sense, an idea of how to do this, to improve this. If you replace if you can get an estimate of how much you get in improvement by, for instance, finite element error estimators, you would avoid solving the PDE before actually realizing it was useless. There's other choices you can, for instance, you can choose the set of combinations a priori. There's a lot of discussions here. But in the end of the day, this is this index set that you will get applying this algorithm, this adaptive algorithm to our naval engineering problem. Again, here in vertical, you see the fidelity that I'm sampling, so the mesh where I'm solving the PDE. And in the horizontal plane, you see the discretization, the multi-index set that I'm using for my sparse grid in parametric space. So you see I have a larger sparse grid over the coarser fidelity and a smaller sparse grid on the higher fidelity. And in the end, I get this sampling scheme where different colors signify different fidelities. This is halfway through the execution, and this is the final stage of the execution. But again, you see that there's a much finer sparse grid for the coarser fidelity, and as soon as the fidelity increases, the sparse grid gets less and less refined. Now, MISC is, by now, there's quite a literature on that. There are some convergence results on MISC They are only, of course, for PDEs that are simpler than the one I'm actually using now. So the result that we have are for elliptic PDEs with parametric diffusion coefficient, under the assumption that the solution is Y-analytic, so it's very smooth with respect to the random parameters. There's two different results. One is for n finite, and one is for n going to infinite. But the results are what you would expect, essentially. I can go back to the setting later on. I would rather go to the second method now. The second method is the so-called stochastic radial basis function. It's a different flavor of multi-fidelity surrogate modeling. And I'm going to give you some details here. So as the name said, it's a multi-fidelity stochastic radial basis function. So each fidelity, the surrogate of each fidelity is a radial basis function approximation with power kernel. So this is the expression of my radial basis function. I will have to give you details on how we choose the number of radial basis functions, how we choose the centers, and how we choose the coefficients of the radial basis function. But I want to focus on the kernel parameter first. So this kernel parameter is a number between 1 and 3. 1 would be linear kernels, and 3 would be the classical cubic splines kernel. So that's why 1 and 3 are suitable bounds for this tau. The proposal here is, instead of choosing the tau a priori and then doing everything with 1 tau, the idea was to actually keep tau as, if you want, a hyperparameter. So it's a stochastic, it's a hyperparameter, and we treat it as random in a sense that we repeat the analysis for several values of tau, and then the final surrogate model is the average of the surrogate models for each tau. Okay. So because now we have a family of surrogate models parameterized by tau, we can also get, in a sense, what we call prediction uncertainties. So the value of the prediction will be more or less constant depending on tau. So for certain, if we have a large variability of the prediction for over the range of taus, that we mean that we are not really sure about the prediction power of our radial basis function. And we use this to choose the location of the next sampling point. So let me show you an example. So let's say that we have we're still in the single fidelity world for the moment. Let's say that we have these 1, 2, 3, 4, 5, 6 values of our fidelity. We actually query the fidelity over these 5 values. We repeat the construction of the radial basis function for different values of tau, and depending on different values of tau, we get the envelope that is here in blue. The area shaded in blue is the envelope of the different surrogate models. Here, for instance, we have a lot of uncertainty, let's say, on the prediction of the surrogate model, and therefore we say that this is our next training point. Okay. Maybe uncertainty is not the best wording here, but that's how we called it. This is in a spirit of the Gaussian process regression, if you want. And then once you know how to do a single fidelity, you can do also a multi-fidelity approach by stacking up with a telescopic sum multiple surrogate models. So you do a surrogate model for the lower fidelity, and then you this would be this one, the red one. Then you would query the higher fidelity. You would query the higher fidelity over a lower number of points. With these higher fidelity samples, you would be able to build the fidelity of the difference between the low and the high, and then you compute the multi-fidelity radial basis function by summing the delta to the low fidelity. So it's again a telescopic sum construction, if you want. And again, you would need to choose where to put the next sample, looking at the prediction uncertainty. So either here or here. And then again, you would do you would, whether to sample the high fidelity or the low fidelity would depend on a criterion based on a profit. So how much does it cost to solve the high or the low fidelity with respect to how much I would reduce the uncertainty. So how much is this with the uncertainty that I have? Now, another thing that I want to mention is now a couple of details on how we choose the number of centers for our radial basis function, the location, and the coefficients W of the linear combination of the kernels. So the optimal number of radial basis function is computed by leave one out cross validation. So we repeat the analysis for a lot of different cases. For each K, what we do, depending on how many centers we're using, either we have enough centers to go interpolation, or we don't have enough centers, and then we do least squares. Okay, if we have, for instance, 20 samples and 3 radial basis function, we have to do least squares. If you do least squares, then you compute the W here, the coefficient by least squares. Otherwise, you compute it by interpolation. And if you have least squares, you also need to decide where you center your radial basis function, and you do that by k-means, essentially. Otherwise, if you have enough samples, if you have enough centers to do interpolation, then of course the radial basis function are centered at the sample points. A big difference between MISC and this radial basis function is that, as you all know, I mean, MISC is essentially sparse-grid, so the collocation points are already quadrature points, whereas here the collocation points are whatever this adaptive procedure comes up with. So if you want to compute moments of your multi-fidelity approximation, you actually need to compute the integral of the multi-fidelity surrogate model, and again, either you do it by sparse grids or you do it by Monte Carlo. This would be the initial sampling of the stochastic radial basis function, and this would be the final sampling of the parametric domain. Now, I want to give you numerical results because the idea of the work was, let's compare which method is better, if any. And the spoiler is there's pros and cons to each of them, which is the best possible outcome, because that means you can keep investigating both, right? So this is the comparison between the sampling scheme that we get at the end of the day. So if you're familiar with sparse grids, you will recognize here the sparse grid structure in MISC on the left, whereas the stochastic radial basis function sampling is much, let's say, less structured, let's say. And again, you see there's a lot of blue, so a lot of samples on the coarser fidelity, whereas only a handful of samples on the highest fidelity. And here you see the growth of the computational work as MISC and SRBF go by. And you see that in the end, we get like 200 solutions on the coarsest mesh for MISC and 50 on the coarsest mesh for SRBF, whereas you only have 5 solves on the highest fidelity for MISC and 9 on the SRBF. So if you now renormalize everything and account for the actual computational cost, this is the convergence, for instance, in approximation of the expected value of the water resistance as the computational cost increases. The entry cost of SRBF is much larger because due to the initialization procedure that I haven't really described, but trust me, the initialization procedure requires to sample all fidelities. So there's a higher entry cost, whereas MISC starts with only the low fidelity, so you get a lower entry cost. And then MISC sort of, let's say, gets to a decent approximation recently, they say decently cheaply, whereas then what happens here is that MISC doesn't converge to the same, let's say, extent of SRBF, I would say. The reference value is a reference value that we got by doing a very fine PCE, single fidelity PCE approximation of the finest fidelity with 80 calls to the finest fidelity. So we were able to actually do a decent reference solution. But if you know, I mean, this tolerance is more than enough for engineering purposes. Here we are off by 2%, which is decent enough. Now, what happens if you now plot the surrogate model? And this is where you see the problem of MISC. This is the surrogate model of the response surface, the surrogate model for the water resistance. You see that the surrogate model of MISC is way more, let's say, wiggly or wobbly. There's a lot of crispiness in the response surface, whereas SRBF is much smoother. There's a couple of kinks here and there, but it's much better. And what is the problem here? And this gets me closer to the open question. The problem is that MISC, as it is let's say, it's based on sparse grids, so it's based on interpolation. And the solver that we're querying has some, let's say, noise issues. So there's some, the function evaluate, you don't evaluate exactly RT, you get an error, and it's not a discretization error, it's something else, it's a nuisance. It's a pollution by a certain noise that will motivate in a second, and then you are interpolating this noise. And because you're interpolating the noise, then you get this noisy surface. What is this noise coming from? This noise is coming from the fact that we are having a multi-grid solver. And in particular, our multi-grid solver switches from one grid to the next finite grid with certain, let's say, criterion on the residual. But the residual of the Navier-Stokes equation is one thing, and another thing is the actual computation of the quantity of interest. So even if the residual of the run solver is beyond control, that doesn't necessarily mean that the water resistance is under control. It got to convergence with respect to the multi-grid cycles. And in particular, you see here, this is a simulation for low fruit. If you look here, it means that the multi-grid cycle switches to a finite grid before the value of resistance has gotten to convergence. And now if you stop on a low fidelity, you would actually stop here instead of jumping here and going to the next fidelity. So this would be where the lowest fidelity solver would stop. This is where the second lowest fidelity would stop, and so on and so forth. So if you use the lowest fidelity, you see that you stop your solver when you're actually not yet converged with respect to the multi-grid cycles. And this is the noise that actually impacts our surrogate surface. And indeed, if you do, if you take a closer look to the surfaces for each fidelity, you see that the highest fidelity surface is much nicer than the lowest fidelity surface. The lowest fidelity surface has these kinks here and here. And if you now stack them together, because this is what MISC does in a sense, it stacks together different surrogates. If the lowest fidelity surrogate is kinky, then the overall surrogate is kinky, okay? And this spoils a bit the convergence. And it spoils the convergence even more if you try to use the MISC method to compute higher and higher moments. It's really visible here. This is the convergence line of the expected value computed by MISC. The highest moment, you see here, there's expected value, variance, skewness, and kurtosis. The kurtosis is really off. And why is that? Because, you know, if you compute kurtosis by MISC, you would take essentially the fourth power of the samples that you get. And if the samples are off, the fourth power of those samples is even further off. So this is the response surface of MISC for the expected value. This is the response surface for the fourth. No, this is for the second order, but still, this is the response surface for the variance. You see, the noise gets amplified. So a possible way to get around this is, okay, so here you see again, this is the response surface for the second order. This is the response surface for the fourth moment. Really off. So if you really want to do computation of moments, an idea would be, instead of using let's say, the sparse grid quadrature on the samples that you get, what you can do is you can do a Monte Carlo sampling of the initial response surface. So instead of taking powers of this surface and then doing the sparse grid quadrature of this, you do a Monte Carlo sampling of the response surface and then compute higher moments from those samples. And this actually works. It works much, much better. But here you see in blue the convergence of MISC.
And in black, you would see the convergence of the Monte Carlo quadrature would apply to the MISC response surface. So this works, but it's a hack that you do afterwards to fix the results, right? And also, it's not obvious how to choose the number of Monte Carlo samples, right? Of course, sampling with Monte Carlo surrogate model is cheap, so it's not a matter of cost. It's a matter of how many samples. If you use too many samples, you actually end up solving with MISC, with Monte Carlo, these oscillations, which you don't want to see, right? So in a sense, Monte Carlo acts as a smoother, but not if you use too many samples. But if you don't use enough samples, then you're just off. So there's a delicate balance here. It's not obvious how to, what is the optimal number of Monte Carlo samples that you have to take on a surrogate model. Then, but this works at least. And then if you compare with the results of the SRBF, I mean, they are sort of comparable. I wouldn't say that one is better than the other. And if you take a look instead at the PDF that you get by sampling the surrogate model for MISC and the surrogate model of SRBF, even though the surrogate model for SRBF, which is this one, is much, much nicer than the surrogate model for MISC, I mean, the bulk of the result is there anyways, right? So this spurious peak, again, is due to the fact that the MISC has problems with the noise of the runs solver being interpolated, but the peak is pretty much okay, and the support of the PDF is pretty much okay. So for most practical purposes, it wouldn't be too bad anyways. This would be the convergence of the CDFs, and again, everything seems to converge to, let's say, to engineering reasonable tolerances. So this brings me to my conclusion. So the conclusion is that actually, as I was spoiling you, both methods are viable alternatives for realistic problems, in a sense. MISC has an edge on getting reasonable estimates at smaller cost. I think that I haven't commented on, but I want to mention at this point, is that I only gave you plots in terms of sheer computational cost, in terms of how many samples of the run solver on which mesh, but there's also an overhead. That would be the amount of operations that you need to do to build the MISC and to build the SRBF. And the amount of operations to build MISC are very easy. You just need to compute the Lagrange interpolant. The amount of operations for the SRBF is actually more demanding because you have to test several number of centers, several number of taus. You need to do the k-means. So there's a lot of overhead costs, which is, I would say, not negligible. So even if, I mean, it's not obvious which is best in terms of computational costs. Certainly, the SRBF has an edge on robustness to the noise. Therefore, we want to improve on both these points. We want to improve the initialization procedure of SRBF to lower the entry cost. And we definitely want to improve MISC, make it more robust to numerical noise. And then also, in perspective, on the long run, we would like to use either of the two methods on optimization under uncertainty. And again, you cannot do optimization under uncertainty if your response surface is wobbly. So we need to do something there, really. And that's actually my open questions for the audience. So how do we actually deal with noise in MISC? I mean, of course, you can say, okay, just drop MISC and move to a more least squares oriented problem, more MISC, let's say a least squares oriented method, but you know, least squares are not necessarily easier to do, right? You would need to then study carefully how many polynomials you can fit with how many samples. I mean, I don't necessarily want to enter that business. So let's try and fix MISC if we can. So one approach that we are currently investigating, or we would like to investigate in the near future, is we could sort of smooth out this roughness on the surface. And one way to do that would be to computing the polynomial case expansion coefficients of the response surface, and then pruning or smoothing the higher frequencies, right? You drop the higher frequencies, or you you catch the trend on the lowest frequencies and then try to take the highest frequencies to where they should. You could do smoothing operators like mover averages, apply Laplacian operators, slope limiters. You could try and, instead of doing MISC with just interpolants, you could tensorize an interpolant plus a smoother. You could penalize the fidelity if the profit doesn't scale or if the total variation of that fidelity is too much. You could try to do an opticom approach, for those who know what opticom is in terms of in the context of sparse grids. And again, penalizing the wobbliness of the fidelities. So there's a lot of things that we can possibly investigate, but I'll leave you there with these open points, and I'm gonna thank you for your attention now. And this is the paper that we prepared on this. It's out since January on this journal here, Engineering with Computers. And thank you for your attention again.